Alright, so this is my video for the Chapter 15 homework assignments that we're working on right now. And for this homework assignment, I'm doing the problems in reverse order because that's how you recommended to do it with the videos that you created for us for the course. And so the first problem I did here was problem number 10 because of that reverse order, and then we'll work backwards until we get to the first problem, number 1. But in problem number 10 here we have this diagram, and it looks kind of like a caster or a wheel of some sort. And so we know it's a 3D problem, and there are two omega values. There's omega 1 here where this shaft is rotating, and then there's an omega 2 where this wheel here is rotating. And the problem wants us to find the acceleration of this point on the wheel, point P. And so the first thing I did was just write out the complete acceleration equation for general motion, for relative motion of a rotating frame that we have, which is right here. And then I just tried to think through the problem and look at what will cancel out. And so we know that the Coriolis term will cancel. We know that this term here will cancel as well because the radius of P on this wheel is not changing. P is fixed to the wheel. And for the same reason, the acceleration of A here will be 0 as well. And so canceling out those terms, I just rewrote the equation here. And then I tried to find each of these terms that we need because we're trying to find the acceleration. And so that's what I did over here. So we know I called the center of our rotating frame here point A, and I labeled that. And so I created this vector with P with respect to this origin A, and we're told that this angle theta is 30 degrees and the radius is 3 inches. And so I converted that inches into feet by dividing by 12, and then broke it into components along the x and y direction. And so that gives us the 3 inches times cosine in the x direction, and then 3 inches times sine 30 in the y direction for that vector. And then for our omega term, we know that there are two omegas that affect this point P. And so the omega will be omega 1, which is, if you use the right-hand rule, will be in the positive I hat direction. And omega 2 will be in the positive k hat direction, or z direction. And so that's our omega term. And then we also can calculate our alpha term right here by doing this cross product. And so we cross omega right here with this omega 1, and doing those cross products we can find out that our alpha term will be negative 20 in the j hat direction. And so once I found all of those, we now have all of these terms that we need, and we can just plug them in and compute all of these cross products. And so this line here, I just plugged in all of those terms that we found, and then this is the cross product for this first term. I did the cross product inside the parentheses, and then cross that with this term here. So this is the result of the first cross product, and then after the second cross product we had this. And then it was just a matter of this addition here, so we just had to combine like terms. And so we had two k hat terms that could be combined, which gives us this final equation for the acceleration of point P on the rim of the disk, and that is in feet per second squared. Okay, so this is problem number 9, and in this problem there were quite a few different steps we had to go through to get to the final answer that it wanted. So basically in this problem we have this collar at P here that's able to slide on this rod from B to D, and then we also have it pinned to AP, this bar here, and we're told the angular velocity and angular acceleration from A to P here. And so the first thing I did looking at this problem is we know that we need to find the angular velocity of the rod attached to B here. And so we weren't given very many dimension measurements here, and so the first thing I did was convert this 200 millimeters into meters, and then we had to use geometry with all of the angles given here to try and figure out the distance from A to P and also the distance from B to P. And so I used the law of sines here to calculate those, and those are the answers I came up with there. And then once that was done, I know in the formulas we're going to be using, we also needed to calculate these two as well. And so just looking at the geometry here and using trigonometry with these angles, we're able to find out what P with respect to A is and what P with respect to B is, because we're going to need those as the problem goes on. And then right here, these are just what was given in the problem, our omega and alpha values for our velocity and acceleration, angular velocity and acceleration. And then this is the equation here that we know we can use for general plane motion, because a lot of the other terms cancel. And then we can also cancel out velocity at A, because we know that this point here at A is pinned. It doesn't translate at all. And so crossing that out, we know that the velocity of P here is omega cross R. And so using the R that we have here and the R given omega, we're able to calculate what our velocity at P is. And then it's just a similar process here to figure out the acceleration at P. And so that term cancels out again, because once again A is not translating. And the acceleration does have some more terms here, but it's just a similar process. We have our omega and our R term, and so doing these cross products and adding like components, we can come up with this as our equation for the acceleration at P. But that's not what the problem wanted us to find. The problem wanted us to find the angular velocity and acceleration of this rod attached to B. And so now we have the acceleration and velocity for point P, but we need it for this rod. And so what we can do here is use this equation here. So we know that the velocity at P equals Vp prime plus the relative velocity. And so Vp prime is basically at that instant. And so what we can do is solve for Vp prime as well, in the same way that we solve for Vp. And so this is what I got when I put that cross product into my calculator. And then looking at this equation, we know we have two of these terms. We have the velocity at P and the velocity P prime, but we don't have the relative velocity. And so in this equation, we still have two unknowns. There's the angular velocity that we're looking for of the rod attached at B, and this relative velocity that we do not know. And so in order to solve this problem, what we can do is break this single equation that we have up into I and j components, and then we have two equations with two unknowns, and we can solve for that. And so what we do is we take our velocity at P equation here, the I and j terms, and they go here and here. And then Vp prime, which is these two terms, come down to here and here. And then our relative velocity broken down into components. If we look at this diagram here, we know that this angle is 70 degrees. So this angle here must be 20 degrees. And so taking the cosine of that in the I direction and the sine of that in the j direction gives us this equation. And then we can just solve this system of equations here for omega and our relative velocity. And so that is our omega term right here. That was the first part the problem wanted us to find, and we know that that is in the k-hat direction, and it came out positive, so our assumed directions were correct. And we know that that is in radians per second. And then our relative velocity is here. And then we'll be using this to find the second part of the question, which was the angular acceleration of the rod attached at B. And so then we have this equation here, which is very similar to the velocity equation we used here, except we also have our Coriolis term as well. And so doing a similar process, we can take this equation and plug in what we know and break it into I and j components to give us two different equations. And so that's what I've done here. I've just taken the information we have from our accelerations and plugged it in to find our I and j equations. And then we have three unknowns here, but we have our relative velocity from the velocity here. And so we can use that to solve for alpha, and when we get our final answer for alpha, we find that that is 81.1 radians per second squared, and that is in the positive direction. Okay, so on problem number 8 here, we have this drum that has this centerpiece bolted onto it, and we are given the radiuses of these two different circles, as well as the velocity and acceleration at D. And so to solve this problem, the first thing I did was just visually look at it and try to understand how it was moving from what the problem said, and then try to figure out what we can deduce about the velocities and accelerations of some of these points just by observation. And so by looking, we know that the velocity of D here will have to equal the velocity of B because they're connected, and the acceleration of D on this rope is the acceleration in the tangential direction of B, and then B will also have a normal towards the center of the circle here that we'll have to account for. Looking at the circle, we can also say that the acceleration at A will be 0, or the velocity at A will be 0, not the acceleration. And because of that, we can say that this is the instantaneous center of zero velocity, and so that's the point we can use quite a bit in our calculations. And so what the problem wanted us to find was the acceleration of three different points on the drum, the acceleration of A, B, and C. And so to start out with the given information we have here, I decided to try and find what omega was for this drum here, because that omega will be the same for any point on this drum, and that's the same for the acceleration because it will all be turning and accelerating at the same amount. And so what I did was use this equation here for the general motion, general planar motion that we know, and we know that A has a velocity of 0, and so we can say that the velocity of B equals the velocity of A plus omega cross the distance between A and B. And we know the velocity of B and the velocity of A is 0. And so by using that equation, we can find out what omega is. And so omega is -4 counterclockwise, or 4 radians per second clockwise. And so now that we have omega, I decided to try and find the acceleration at A. And so this is our general plane motion equation for acceleration. And looking at this equation, there's quite a few unknowns in here that we don't know. However, if we break it into components, we can actually solve for alpha. And so I took this equation and plugged in what we know. So we know the acceleration of B in the I direction. And then we also know some of these terms here. We've calculated omega from above, and we know the distance between them. And so pulling out from this equation just the components in the I direction, we can have the 0 acceleration of A in the I direction. has to equal negative 30 plus 2 alpha, and so using that we can solve and find that alpha is 15 radians per second. And then after that I used the same equation once again to find the acceleration of A, but this time I did it from the center of these drums at point G. And so it's a similar process here. We just plug in the things that we know. The distance between A and G is the 3-inch radius here. And we solve for alpha up above, and we solve for omega up above as well. So now, plugging all that in, we can look at the I and J components once again. And so in the I direction, we can actually solve for the acceleration of G, which is not one of the accelerations the problem asked us to find, but we can use it later on as we solve for them. And then in the J hat direction, we know omega, so we can actually solve for the acceleration of A, which comes at 48 inches per second squared J hat. After that, I went up here and started working on the acceleration of B, because we found this one, so we need B and C now. And so I once again wrote out the general plane motion equation for acceleration. And at this point we actually know everything in this equation. There's no unknowns except for the acceleration of B, because we calculated G, alpha, and omega over here. And so all I had to do was plug in those terms and then combine like components or like terms, which gives us this for the acceleration of B. And then once again repeating that process for the acceleration of C, and then relative to point G here, gives us this same equation here. And then once again we can just simplify this and combine like terms to find the acceleration of C. And so those are the 3 accelerations that the problem wanted us to find. And then looking at that, we can do kind of a quick check to make sure our answers make sense. And so looking at this wheel here as it rotates, if we look at point A here, it makes sense that there will be no acceleration in the I hat direction, but as it turns there will be a centripetal acceleration towards the center of the circle, which is what our answer reflects here. And then if we look at point B here, we know as this wheel turns, B will travel this way, going up and to the left. And so that gives us a negative I hat component and a positive J hat component. So that also makes sense. And then once again for point C here, as this drum travels, point C will go down and to the left. And so we have a negative I hat component and a negative J hat component. And so those are the answers for part 8. For question number 7 here, the problem wanted us to find the acceleration at point A right here and the acceleration at point D. And so to start off with, I just looked at the problem here and kind of tried to find out what velocities would equal 0 while looking at it. So we know that the velocity of this crank BC here is constant, and it has a velocity of 45 rotations per minute. And so the velocity of point C right here will be 0, and the acceleration will also be 0. So that will be an instantaneous center of rotation for this bar here. And so this is also in rotations per minute, and so right here to find out our omega for this bar, I just converted that into radians per second. So the units would match, and we know that it comes out to negative 4.71 radians per second, and it is negative because we know it's in the clockwise direction. And then the first thing I looked for was the acceleration of B, because I figured if I could find the acceleration of B where it's connected here, then I would be able to find the acceleration of A and D. And so this is the general plane motion equation for the acceleration at B. And then looking at this, there's quite a few terms that will cancel. We know the acceleration at C is 0, and we also know that the omega is constant. We have a constant angular velocity, and so this alpha term, our angular acceleration, will be 0 as well, so we can cancel both of those terms. And that just leaves us with this final term here. So plugging in the omega that we converted there, and then the distance here, that gives us angular velocity of 88.73, or an angular acceleration of b of 88.73. And then from there, I decided to go down this way and try to find the acceleration of point A, which was the first thing the problem wanted us to find. And so I rewrote this general plane equation for acceleration in terms of points A and B. And now we have the acceleration of B, so we can plug that in. We don't know alpha yet, but we can find this distance here between A and B. And so what I did is broke this into components. So we have these dimensions here. So using the cosine of this angle in here, we can find the height in the j direction. And so the distance between A and B is 4I hat plus 4 root 3 j hat. And then we can compute this cross product here, and a similar process here. And then we have more unknowns than equations here, so we need to break it up into our components. And so in the I hat direction, we know the acceleration of A in the I hat direction will be 0 because it can only move up and down in this track. And so because of that, we're able to solve for alpha. And so that gives us a value of alpha of negative 12.75 radians per second squared. And then doing the j hat direction, we have acceleration of A equals 4 alpha. And we solved alpha from the I components, and so multiplying alpha times 4 gives us our acceleration in the 4A in the j direction. So it is traveling down at 51 radians per second squared. And then we need to repeat a similar process for the acceleration of point D. The difference here is point D is not trapped in this track, so it will have acceleration in both the I and j directions. And so taking this equation here, we plug in what we know. So we know the acceleration of B from above. We just barely calculated alpha here. And then we can do a similar thing for the R term here, breaking it into components. So we have 16 sine 30 and 16 cosine 30. And then our final term, omega squared r. And so looking at this, we have everything we need to solve for the acceleration of d. So it just becomes a matter of doing this cross product here. So here's the work for that cross product that I did, which gives us these two terms. And then it just became a matter of plugging in our alpha that we solved for and combining our I hat terms to give us our acceleration of d. And the acceleration of d here that we got for our answer does make sense. If we look at this, as point A goes down, we know that point D will accelerate to the right and down. And so that is the correct answer there for part B. Okay, so this is problem number 6 here. We have this diagram with these 3 different gears in it, and they're all hooked to this arm here, ABC, that rotates. And we're told that the arm ABC rotates counterclockwise with 4 radians per second, and that it's going to be fixed here at B. And we're also told the angular velocity of gear B here is 8 radians per second. And so in order to solve this problem, the first thing the problem wanted us to find was the instantaneous centers of rotations of gears A and C. And we know that the instantaneous center will be where the perpendicular lines from the velocities will cross each other. And so in order to find that, we have to draw the velocity arrows. And just looking at this diagram and thinking it through, though, we know that if we draw the velocity of C will be vertical in the j direction, and the velocity from point B to C where they touch here will also be vertical. And so since all the velocity vectors will be parallel to one another, what we're going to have to do is draw two velocity arrows and then draw a triangle and use geometry like similar triangles in order to find out where that instantaneous center is. And so I decided that I would need a lot of the velocity values at different points. Like we're going to need the velocity at A and C and in between these points. And so I started by just calculating a lot of those different velocities. And so this is the equation I used to find the velocity of C. And we know that the velocity of B is 0. And we were given omega for this arm. And the distance between B and C was also given. And so calculating that, we know that the velocity of C will be 1.2 radians per second, and that has to be in the j-hat direction. And then it's pretty much the same calculation for the velocity of A, except we know that A will be traveling down in the negative j-hat direction. And so after that, I also found the point where gears A and B touch each other, and I called that point H, and calculating that we can find the velocity there is 1.6. And so then I just drew this triangle here to help give me an idea of what the triangle was, and drew the triangles to kind of think it through. And so we can find omega by taking the difference between those velocities that we calculated and dividing by the radius of the circle, which gives us a value for omega A of 4 radians per second, and that has to be clockwise. For the instantaneous center of gear A, we can use that same ratio of omega VA over omega A, and we can find that the instantaneous center has to be out here 0.3 meters to the left of A, and it has to be directly in line with A because it's perpendicular to the velocity vectors. And then it's just a matter of repeating this again for gear C. And so I drew the diagram for gear C. I called the point in between here point J, and calculated the velocity of J to be 0.8 meters per second. And so finding that, we can find that omega C has to be, once again, the difference divided by the radius, which gives us 2 radians per second counterclockwise. And then using all those values, once again, we can find that the instantaneous center for C is 0.6 meters, and that is to the left of C, as you can see in the diagram here. For problem number 5, we have these two wheels that are rolling along this horizontal surface, and we're told that they're not slipping. And they're also connected by this rod AB that's 14 inches long. The question wants us to find the velocity of point E right here. And we're given the radiuses, the distance of this rod, and we're also given the velocity of D right here, which is 6 inches per second. And so in order to solve this problem, the first thing that I did was I took the velocity of D that we were given, and I tried to find the angular velocity, omega, for this first wheel. And so looking at this, we know that both of the points where the wheels touch the ground will have a velocity of 0. And so I labeled those so we could use them as we do our calculations. And so using that point and point D, we know that this will be 0, like I just explained. And we're looking for omega. We were given D, and R between D and the ground is just the radius of 6 inches. And so running that calculation, we find that the angular velocity of this first wheel is just 1 radian per second. And then I used that to find the velocity of this point A here. So I'm trying to kind of work my way from our given information at D to this wheel over here. And so by finding this point here, we can work our way over to E, the point that we're interested in. And so using that same point here, we now know omega because we just calculated that. We can find out the velocity of A, and that comes to 11 inches per second. And that makes sense because omega is 1 and the distance between the ground and A is 6 plus 5 or 11 inches. And then after we have the velocity of A, we can use that to try and find the velocity of B to get to the other wheel here. And so I wrote this equation here, the same equation, but with two different points. And so the velocity of B has to equal the velocity of A plus omega of this bar times the distance between A and B. And so what I did was I took this distance here and broke it into its components in I and J, and then we have this equation here, but the problem is it still has too many unknowns and we can't break it into components yet because the velocity of B might have velocity in I and J directions. We don't know yet. And so that was all we could do there. So in order to solve this, we had to come up with another equation. And so looking at this here, we can use this point where the velocity is 0 to try and find another equation for the velocity at B. And so we have this equation here. This is the point on the ground that is 0. And this is the radius. The R value will just be in the J direction and the I direction. So we have, it goes -4 in the I direction and up 6. And so our second omega has to equal, our second omega crossed with those components has to equal velocity of B. And so simplifying that, we get this equation here, and now we have two equations that we can work with. And so what I did was finally I broke these into components here and set them equal to each other. Set this equation equal to this equation because they both equal velocity of B. And so solving that, we can find out what the angular velocity of both of these wheels are. So we find that the angular velocity of the wheel with center E has this point B on it is -2.46, and the omega for this rod is the 0.753, and we found the omega for this wheel over here was the 1 radian per second. And so the problem's almost there now, but we still have to find the velocity at point E, and that's we know the angular velocity, but we need the velocity. And so we go back to this equation here, and I decided to go from this point that I created here because it's 0. It makes our calculations a little bit easier. So we can plug in the angular velocity of the ball that we just found, the wheel that we just found, and we cross that with the distance here, which is just the radius of 6 inches. And so running that calculation, we find that the final answer for the velocity of E is 14.76 inches per second, and that is in the I hat direction. So for problem number 4 here, we're given this diagram and we're asked to find the velocity at A and the velocity at B. And so the first thing I did was just pull out the information that was given to us in the problem. So we know that the angular velocity of this rod DE is 2.4 radians per second, and that is clockwise. And we also know that the velocity at E here will be 0 because it's pinned, and so we can use that to our advantage. And so the first thing I did was try to find the velocity here at D where these two bodies are connected. And so using our equation that we know here, we know that we can cross out the velocity of E because it's pinned, it's 0. And we're given omega and the distance here, which I just converted from millimeters to meters. And so doing that cross product, we get the velocity of d is 2.88 meters per second, and that has to be up in the j hat direction. From there, we can try and work on finding the velocity of a. Looking at this diagram here, we know that the velocity of a has to be either I hat or negative I hat, because it's this collar here that's running through this rod, and so it can't move up and down. And so that will help us to be able to solve that. So using the same equation here, we plug in the velocity at d that we just found. We don't know the omega yet, but we can find that here. And then we cross that with from the distance from d to a, and I broke that into components, and so we have 150 millimeters in the j hat direction and 80 millimeters in the I hat direction. And so that's what this term is here. And then after we complete that cross product, it leaves us with this. And then, like I said, we know that the velocity of a has to be in the I hat direction. And so if we break this into components, we can set the j hat direction equal to 0. And that leaves us with only one unknown of omega. And so when we solve that, we get an omega value of negative 3.6 radians per second. And then we have our equation here in the I hat direction, and we can plug in the omega that we found and solve for the velocity of a. So the velocity of a comes to 5.4 meters per second in the I hat direction. And then the second part of the question wanted us to find the velocity of b, and since we already know omega, that makes this a little bit easier. So we write this equation here in terms of trying to find the velocity of b with respect to d. And we have everything we need here except for calculating the distance from d to b here. We were given that this is 60 millimeters, but we don't know this distance here, and so I just used similar triangles from what we found in part A to find the distance here in the I hat direction, and then I computed the cross product of omega cross r, which gives us this equation here. And then all we had to do was combine like terms to get our final velocity of b is negative 2.16 I hat plus 4.032 j hat meters per second. And so that's the answer for part B. So for problem number 3 here, we're given this disk and we're told that it's moving in the xy plane, and so we know that we have planar motion. And it gives us the velocity, some of the components of the velocity of 3 different points on this circle here. It asks us to find the angular velocity of this disk, omega, and it also asks us to find the other component of the velocity at b. And so in order to do this problem, I just first started by writing our general equation for planar motion here. And I tried to find this velocity and omega. And looking at this, we know that the distance from b to a is 0.6, negative 0.6 I hat and negative 0.6 j hat. I drew this triangle over here to kind of help me think that through. So we know those components. And then looking at the problem, we realize that we have components in one direction but not the other. So if we write this equation and then break it up into components, we'll be able to solve for the pieces that we need. And so taking this equation here and solving the cross product gives us the equation we need, and then this is what I did, breaking it up into the I hat and j hat directions. And after I did that, it didn't really help me to solve the problem at this point because I still had 3 unknowns and 2 equations, the velocity of a in the x, the velocity of b in the y, and omega. And so I had to do this equation again for another point. And looking at the given information, I realized that we had the velocity of b in the x direction and the velocity of c in the x direction, which means our only unknown for that equation would be omega. And so that's the one I decided to do next to help me find omega. And so that's the work I have here. We have our distance between B and C in components, and then breaking that up into the I hat direction, our only unknown is omega. And so we can solve for our omega value of 10 radians per second. And then I took that omega back up here and plugged it in to find the velocity of B in the y direction, which we needed. And so that gives us a velocity of by of -1 meter per second j hat. And then we just combine that with the velocity that was given to us in the x to give us what the question was asking for. The velocity of point B is -7.4 I hat minus j hat. Alright, so on this problem number 2, we're given this load here that's attached to these gears. And as these gears turn, the load will be raised, and we want to raise the load up 20 feet. And we're given that gear A here is initially at rest, and then we're given its uniform acceleration until it reaches a steady state of 120 rotations per minute. And so looking at the problem, we know we're going to have to use our equations for constant acceleration, because our acceleration is either constant or 0. And so the first thing I did was just write out the information that was given to us. We're given the speed in revolutions per minute, rotations per minute. And so the first thing I did was just do a unit conversion to get that into radians per second that we could use. And then I wrote down this equation, which we had to use quite a bit to solve this problem. And so we know that the change in height of the load here has to equal the number of radians that this wheel turns times its radius. And so using that equation, we can find out how much this wheel B needs to turn in order for this load to raise 20 feet. And so in order to solve that, the first thing I did was rearrange this equation here. And I multiplied our 20 feet by 12 to get it into inches, and then divided by the 15, which is the radius of this portion of B that's the rope is winding around. And that gives us a total of 16 radians to lift the load. So that's how much this wheel B needs to turn, gear B. And then from there, we needed to find out, the question was asking for the number of revolutions by gear A. And so this is basically just a ratio. And so using this same equation, we can plug in what we know. We know the radius of B, we know the radius of A, we know the theta value, the number of radians for B, and so we can solve for the radians for A, which comes out to 96 radians. And then all we have to do from that point is do this same unit conversion to put back into revolutions. And so the answer for part A is 15.28 revolutions. So that's how many times A needs to turn. And then for part B, we're asked to find the time required to raise the load. And so in order to solve that, I kind of looked at it in two phases. So there's the portion of the problem where there's an acceleration until it reaches 120 RPM, and then after that we know the acceleration is 0 until the load is raised the 20 feet. And so for the first part of that, with the acceleration, we're given the initial angular velocity and the final angular velocity, and so we can use our constant acceleration equation to solve for alpha. And so this is just the equation where we use omega final has to equal omega initial plus alpha times our delta t. And so that gives us an alpha of 2.51 radians per second squared. And then using another one of those constant acceleration equations, we can solve for the final theta, so how many turns it makes in the first 5 seconds with the acceleration. And so we know that the initial omega is 0, and so that term cancels. We also know that the initial theta is 0, so that term is 0. And we're given everything else we need. And so plugging all of that in, we know that during the acceleration phase of this problem, the the theta final will be 31.37 radians in the first 5 seconds. And so the problem wanted us to find the total time, basically, and so we can take this number and subtract it from the total theta that gear A needs to turn. And so that's what I've done here, which gives us how many radians we need to turn during the constant acceleration equaling 0. And so all we had to do on this is, since the acceleration is equal to 0, we know that the velocity will be 4 pi radians for every second. And so dividing 64.625 by 4 pi gives us the total time to raise the load the remaining amount. And so that gives us a time for the second phase of 5.09 seconds. And then to find the total time, we just have to add that to the 5 seconds that was given, which gives us a total time of 10.09 seconds. So that's the answer for part B. Alright, so on this problem we have these two different pulleys here. They're operated with this belt around them, so it could be like a lathe or some tool like that. And we're asked to find the time for each of these different positions for the omega of B to reach 400 RPM. We're given the angular acceleration of shaft A, and we're also told that it starts from rest. And so in order to solve this problem, the first thing we had to do was create an equation using some of the relationships that we know. And so I took this equation here. We know that the linear velocity has to equal omega times r, the radius. And since the velocity of this belt is the same, we know that r omega A has to equal rb omega B. And so we can rearrange this equation to solve for omega B, which is what we were given. And then we also need to replace omega A with the alpha term here, so we have a term that has time in it because we're looking for time. And so we know that omega A has to equal alpha times t. And so replacing that gives us this equation here. We can divide alpha by omega to give us this term. And our omega value here was given to us in RPM again, and so we had to multiply by 2 pi over 60 to turn that into radians per second. And then we take this omega term and we divide it by alpha to get 6.98. And then we have this really nice equation here that relates the radius of A over the radius of B times t has to equal the 6.98, which is the omega that we're looking for, omega B. And so then it just, all we have to do is plug in the different radiuses for the 3 different positions here and solve for the time. And so in the first position, the radius of A is 2 and the radius of B is 1. And we can solve that for t and find that the t is 3.49 seconds for it to reach that, for B to reach the RPM that we're looking for. In position 2, the radiuses are actually the same, and so this term is just 1, and the t turns out to be 6.98 seconds, so it will take A the same amount of time as it would take B to reach that omega value. And then for part C, or position C, the wheel would be here, so the radius of B would be larger, and so it would be 1/2 times t. And so multiplying this by 2 gives us our time for the third position, which is 13.96 seconds. Okay, that's all for this homework assignment. Thank you.